Welcome to Unit 5. Unit 5 is, you need to read sections 1.9, 10, and 11 prior to reviewing the slideshow. This is a fairly stout unit. We'll talk some more about some units and unit conversion types of issues in here. In Unit 4, we talked about the SI system of units. We had meters and kilograms. We had the 7 basic units. This unit, we're going to expand that and talk about what are called derived units, units that come from those particular measurements. The examples we'll see in particular are area and volume units. We'll look at density. We'll also look at temperature scales and how we get back and forth between them, and also just a touch on energy units and their interconversion. Think about area for a minute. This is section 1.9. In the box on the left-hand side, you see a box, a square that's 1 yard on each side, 1 yard tall, 1 yard across. If you want to know the area of that box, the way you're probably where we would do that is to take and multiply those two dimensions together. So we take 1 yard times 1 yard and get 1 square yard. If I think of the box differently, as I have it on the right-hand side, and I look at taking that same size box, and instead of thinking about it as 1 yard on each side, thinking about it as 3 feet on one side, because that is a legitimate replacement for 1 yard. In that box, the area would be 3 feet times 3 feet is 9 square feet. Notice that means that 1 square yard, that box on the left, is equivalent in area to 9 square feet. Not to 3 square feet, but to 9 square feet. I had to take and square that dimension. If we extend that and look at volumes a little bit, so there's a block drawn there on the right-hand side, and that block is 1 yard on each side, and I've broken it into 1 foot segments, so there's 3 1-foot segments on each side. If I want to find the volume of that block, I would take the length times the width times the height. If I think of it in terms of yards, that's 1 yard times 1 yard times 1 yard is 1 cubic yard. If I took and I measured it in feet, then each side is 3 feet, so it would be 3 feet times 3 feet times 3 feet, and the area would be 27 cubic feet. The volume would be 27 cubic feet. So that tells me that 1 cubic yard is the same thing as 27 cubic feet. Notice it's not the same as 3 cubic feet. So I have to pay attention in my dimensions. I'm going to take and square them or cube them. I need to pay attention to that in looking at my conversions. So if I switched over from our familiar yards and feet, now this works the same way in the metric system. There's really no difference at all. I'm just, instead of measuring the side of a box in yards or feet, I'm going to measure it in meters or centimeters or millimeters or something along those lines. If you look at the examples that I have down below, 0.55 meters, I want to convert that into centimeters. You know how to do that. You're an expert at that from Unit 4. Is it's a 2 decimal place change, and I have to move it to the right because I'm getting to a smaller unit. And so it becomes 0.55 meters is the same thing as 55 centimeters. What happens in my area and volume conversions is now I have to take and either double or triple the number of places I move the decimal point. So if you look in the second example, 1.98 square meters is equal to 19,800 square centimeters. Think of it this way. If I want to go from meters to centimeters, it's a 2 decimal place change. If I want to square that, it's going to be a 2 times 2 is a 4 decimal place change. So again, I'm going from a large unit to a small unit. I'll move it to the right, and I'm going to move it 4 places because I'm squaring that dimension. And the very bottom one is an example of volume. If I'm going from cubic meters to cubic centimeters, again, it's a 2 decimal place move for each meter to centimeter conversion, but I have to do that 3 times because I'm cubing it, and so I have to move it a total of 3 times 2 is 6 places, and so I take that decimal place and move it 6 decimal points to the right. In making these conversions with these derived units, these squares and these cubes, don't forget that conversion factor has to be multiplied, it has to be squared effectively is what we're looking at. Let's go a little bit more with metric volume. Think about it this way, because very common units in metric volume that we use in sort of everyday, especially health-related types of life. If I think about a box that's 1 meter on each side, and a meter is a little bit bigger than yardsticks, so it's a pretty big box we're talking about, it would have a volume of 1 cubic meter. That's a pretty difficult unit to work with. You think about things you see in everyday life when you go to buy pop bottles, you buy 2-liter pop bottles, things of that nature. If we did those in cubic meters, those would be like 0.002 cubic meters. Nobody's going to buy a 0.002 cubic meter pop bottle, or I guess you could call it a 2 millicubic meter. Nobody's going to use that either. So what we do is we take that idea of the cubic meter and say, okay, let's get it to a little more convenient unit. The common smaller unit we use is called the liter. Okay, the L-I-T-E-R, you also see it spelled L-I-T-R-E. A liter, abbreviated with capital L, is defined to be the volume of a box that is 1 decimeter on each side. Okay, so that means it's a box 1 decimeter on each side. It's 1 times 1 times 1 is 1 cubic decimeter. Remember, a decimeter is 1/10 of a meter. And so when I think about it in that sense, that in a cubic meter I actually have 10 times 10 times 10, or I've got 1,000 of these cubic decimeters, or 1,000 of these liters. And so I can think of the liter as being 1,000th of the volume there is in a cubic meter. We go a little bit further with the liter because we very often use it in a smaller unit. And a natural thing to say and to think about is if I took 1,000th of a cubic decimeter, or 1,000th of a liter, since a cubic decimeter and a liter are the same thing, that 1,000th, using our metric prefix expertise, would be a milli. So I took 1,000th of a liter, I can call it a milliliter. Okay. I can also, if I think about the length terms, think of it as the fact that if I have a box that's 1 decimeter on each side, it has 10 centimeters. So it has 10 times 10 times 10. There's 1,000 cubic centimeters in 1 cubic meter. So you'll see the terms cubic centimeter, the term milliliter, and you also see the term cc. If I heard of that, you'll see those things used interchangeably because they are representing the same volume. So how do I convert between volume units if we don't have these simple blocks and cubes and all that kind of thing? So let's take a look at how this conversion can go on. We aren't going to do the whole world's worth of conversions, but let's take a look at some that are relatively important to us. Volume is one of the ones we're very interested in. As I said in the previous slide, 1 liter you could also talk about as being 1,000 milliliters, and that's just a simple metric conversion. If you look at it, I'm going from a big unit liter to a milliliter. I'm going to move it 3 places because of milli, and I'll move it 3 places to the right, and so I get to 1,000 milliliters. The other way of referring to a milliliter is a cubic centimeter, so 1,000 milliliters is the same thing as 1,000 cubic centimeters, and that's the same thing as 1,000 cc's. Okay, so the milliliter, cubic centimeter, and cc are all the same thing. Now consider the following conversions. Let's look at some volume conversions here. These are again fairly simple early on as far as metric goes. Milliliter to liter. Milli is a 3 decimal place move. I'm going from a big to a small. From a small unit to a big unit, so I'm going to move it to the left 3 places, and I get 0.546. If I look at the next one, I'm going from a large to a small, so it's going to be 3 places again, but now it's going to go to the right and become 1,260 milliliters. If I look at the third one, start with 0.0345 cc's. Remember, cc is the same as a milliliter, if that helps at all. It's a 3 decimal place change, and I'm going to have to make this thing smaller because I'm going to a larger unit, so I'm going to move it to the left 3 places, and you'll see the number written in there. Or if I write it in scientific notation, remember that from a couple units ago, I could write it as 3.45 times 10 to the minus 5. And then the last one is really a whole lot like the second one. The second one was a liter to milliliter conversion. A conversion from liters to cubic centimeters is the same thing because a cubic centimeter and a milliliter are the same units. Okay? Same metric conversions we did back in the previous unit. Let's look at another derived quantity, if you want to call it that. That would be the density. Density, we're looking at the concept of the mass over the volume. You have some sense of density because you know about things floating and not floating, and if something's more dense, it's going to sink than what the fluid is that it's in. You know about those sorts of things. The actual definition of it is given here. Density is the mass divided by the volume. So density relates the mass of the material to whatever its volume is, and we usually express it in units. There's all sorts of units you can use for this. The ones we typically see are grams per milliliter, grams per cc, grams per cubic centimeter. Sometimes you'll see a kilogram per cubic meter, but it's always a mass per volume unit that you're looking at. Now to work with the density, recognize that this equation actually has 3 variables in it. Sounds like math, doesn't it? Density is the mass divided by the volume, has 3 variables. If we know any 2 of those, then we can also figure out what the third one is by using our algebra or some other ways. We're going to look at three ways of handling a problem like this, where we know two of those parameters, we want to find the third. We're going to use algebra, because I know that'll be your favorite way. We're going to think about just thinking it through, sitting back, putting our feet up, and thinking about the problem. And then we're going to look at what's called the unit conversion method, which we'll use later on as well. The algebraic way of working with density is to think of it this way. It's just a formula. It's just like y equals x over b, or something along those lines you may have done in math before. You've certainly done in math before. And so we can think of it in that sense, and then what we can say is, well, if we know two of those variables, we can find the third. It's just a mathematical relationship. The three cases are, in the first case, that I have in the second bullet, I've got the mass and volume are known. If I know the mass and the volume and I want to find the density, that's pretty simple. I take the mass and I divide it by the volume, and there's my density. The density will always have units with it. Grams per milliliter, grams per cubic centimeter, whatever those units are, they have to go with that number, because a number like that in science without a unit is totally meaningless. If I go to the third bullet, if I know the density and the volume and I want to find the mass, there's an algebraic equation there for you too, because what you really have to do is just take and multiply both sides by the volume. Remember that? If I multiply both sides by the volume, it becomes density times volume equals mass, because the volume cancels out on the right hand side. So I can find the mass simply by multiplying the density and the volume together. And then the last case, if the density and the mass are known and the volume is what we're after, we just rearrange a little differently, and I can take what I've done in the bullet right before that, mass is equal to density times volume. If I want to solve that for volume, all I have to do is take the mass and divide it by the density. It's all algebra. We had you take algebra for a reason. You've seen algebra so you can handle these sort of relationships. Do a different approach. But let's do a different approach. So let's think about it for a minute, because some folks are very logical about this kind of thing, and they don't need stinking formulas and all sorts of things like that. And so let's say we're looking at a case up here. I have a density of 1.85 grams. Oh, my point here in the first line is when you see something like grams per milliliter, read that as for each and every milliliter. That means that the mass of 1 milliliter of this substance is 1.85 grams. That's what that means. And it's like when you go to buy gas at the pump, and today it's $3.35 per gallon. It means for each and every gallon you're going to pay $3.35. Well, that's today. I don't know what it'll be tomorrow or whenever you hear this. So now, let's say we have a mass and a volume, we want to find the density. There's nothing fancy about that. That's just using the definition straight away. Density is mass divided by the volume. Take the mass, divide it by the volume. Now, if I have a density and a volume given to me, I want to find the mass. Okay? Then you have to think, before we took the algebra approach and did it, let's think of it this way. The density is the mass for each and every milliliter that you've got. For every one of them. Okay? That's the density. That's the mass. So all the densities, what the density is telling me is there's 1.85 grams in every milliliter. So if I had 10 milliliters, I'd have 10 times 1.85, wouldn't I? And so all I have to do is multiply the volume and the density together to get the mass there is in some volume of it. Go back to gasoline again. It's $3.35 a gallon. If I have 10 gallons, how much am I paying? $33.50. You multiply them by each other. Then the last approach is, if you got a density and a mass and you want to find the volume of it, okay, remember the density represents the mass for each and every milliliter. So if I take my mass that I've got and I figure out how many times the density goes into that, that gives me how many milliliters. And when I say goes into, what we're saying is divide by, isn't it? And so if I take a look at that case, you can say, okay, if I'm going to buy, this is kind of like, let's see, how many gallons of gas can I buy if I've got $50? Okay, well, let's make it an easy number. This is not real, by the way. Let's say it's $5 a gallon, and I have $50 to buy gas with. What do? I take my $50 and I divide it by that cost, divide by the density, if you will, my cost density here. And so I divide the 50 by the 5 and get 10 gallons that I could buy. Same thing in density. You take your density and you divide it, and you can take your mass that you've got and you can divide it by the density of it to figure out how many milliliters you've got. Density is an example of something we call a unit conversion factor. What it really says to us is that whatever we have written on the top is equivalent physically to what I have on the bottom. So if I have a density of 2.45 grams per milliliter, it means each and every milliliter of this substance is 2.45 grams. So I could weigh out a volume of it that's 1 milliliter, or I could weigh out 2.45 grams of it on a balance, and if I were to do that, I'd have the same amount of material. Okay, so I can think of that ratio as really, if I take 2.45 grams of this material and divide it by 1 milliliter, that's equal to 1. Or the other way around, if I take 1 milliliter and divide it by 2.45 grams, it really represents 1. And that's called a conversion factor. Another thing from algebra you might remember is that any number multiplied by 1 does not change in value. So I can multiply a number by 1 all day long and I don't change the actual value of it. So what we do in the unit conversion concept is we have some given measurement that we're looking at, and we want to convert it into some other type of unit. And it can be broader than this. It's not just in units that we're going to use it. We'll use other examples later on. What does it say? Well, it means if I start out with whatever it is I've measured out and I want to get it converted somewhere else, I can multiply it by 1 a lot of times, and I'll multiply it by 1 with unit conversion factors that change my units to where I want to have them be. So let's look at some examples on the next slide. The setup for the unit conversion looks like this. We have our desired quantity over on the left-hand side. We're going to look at an example after this. We start out in here and say, okay, here's what my given quantity is that I'm trying to convert. Then we're going to multiply it by that unit conversion factor. We're on the top of it, we'll put in whatever units it is we want to have over on the end, on the left-hand side. In the bottom of it, we'll put units that will cancel the units in my first term on the right. Yeah, so let's take a look at an example on the next slide. I want to find the volume of 45 grams of a substance that has a density of 3.45 grams per milliliter. Okay, so I've drawn arrows in to show you where everything's coming from and where it looks. And so we come into here and say I'm looking for how many milliliters this is. That's my volume I'm after. My starting measured quantity is the 45 grams. In this particular example, I could have had 50 grams or 70 grams or 80 grams or 100 grams. That number could be anything at all. But the density of it is fixed at 3.45 grams per milliliter. This material always has this density to it. That's a conversion factor. So what I'm going to start with is the given quantity of 45 grams, as the arrow indicates, and put that in that first term on the right. And then when I see those grams on top on the right hand side, it means right away that on the bottom on that conversion factor I have to go to grams. So my gram units will cancel out. I want to come out in milliliters, so on the top of it I'll put milliliters. And if I take 45 grams times 1 divided by 1 divided by 3.45, I get my answer of 13.0 milliliters. Slightly different topic, temperature scales. Well, considerably different topic. 3 primary temperature scales we look at. Which one is the SI? That's right, the Kelvin. I'll just assume you said that. The blue line on the bottom represents the freezing point of water. The blue line on the top represents the boiling point of water. And you note on the Fahrenheit scale that water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Now if I had 3 identical thermometers like we have here, and I hadn't marked them off at all yet, and I just had mercury in them, I put them in freezing water, they'd all come to the same level. And all we're doing here is we're putting different marks at that level. If I'm on the Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit. If I'm on the Celsius scale, the freezing point is 0 degrees Celsius. And if I'm on the Kelvin scale, it's an odd number, but it's 273.15 Kelvin. If I take now those thermometers and I put them in boiling water, what I find out is I'm going to mark off the Fahrenheit scale at 212 degrees Fahrenheit. The Celsius scale, though, is marked off at 100 at the top end. It used to be called the centigrade scale, centi meaning hundredth, right? And so fundamentally what it looks like is the temperature unit between the freezing point and boiling point of water is 1/100th of that difference. And then the Kelvin scale is really kind of special. It's called an absolute temperature scale. And the way it's set up is that bottom number is not something somebody just threw at a dartboard and decided that would be the number. This is called an absolute temperature scale. the 0 Kelvin is the absolute zero in the universe. We can never achieve that temperature whatsoever. We can get close, like within trillions of a Kelvin, that kind of thing. The strange numbers in there are designed in such a way that the size of the Kelvin unit is the same as the size of a Celsius degree. Okay, so let's take a look real quickly at some conversion things. You don't have to memorize these. These are just formulas for converting from between different temperatures. Celsius, Fahrenheit, you just take your Celsius temperature, multiply by 1.8, and add 32 to it. That's a Fahrenheit temperature. Fahrenheit to Celsius, shown there, and the Celsius to Kelvin is pretty easy because you just could take and add 273.15, since those scales are the same size. I might point out that Kelvin is not called a degree. I think I have that in the next slide. Yeah, Kelvin is an example of an absolute temperature scale. Absolute zero is unattainable. We've been close. Oh, sorry, 10 to the minus 12 Kelvin, not trillion or so. So we've been down pretty low, but theoretically we can never get to 0 Kelvin. Another thing to notice, the temperatures on the Kelvin scale are written without the degree sign. Okay, so we'll talk about those units as kelvins. A temperature of 345 kelvins is just written as 345 capital K. And then the last note, I think, in this chapter is heat. To talk about heat, it's a term we use to talk about energy that's transferred due to a temperature difference. That energy is always transferred from the higher temperature body to the lower temperature body. And so you think, okay, leave the door open, it's going to be cold here, all the cold air is going to rush in. That's not the problem. If you leave the door open, all the hot air is rushing out. Okay, it's always going from a high temperature to a cold temperature. Typical units of energy we'll see are called joules and calories. You've probably heard of calories. You've probably think about food calories. A food calorie is actually a kilocalorie. It's 1,000 calories. So if you think about it, if you have a piece of chocolate cake and it's 250 calories, you're more likely to eat that than you are if we write down what it really is, which is 250,000 of the littler calories. And so a food calorie is really a kilocalorie. Plus, you don't want to call them kilocalories because everybody will think they're really, really big, which they are. Now there's a conversion there between calories and joules. That's the end of Unit 5. Unit 5, you'll need to work the self-assessment on it. It will be on Quiz 2 and also eligible for the midterm and the final exam.